Hey, good morning. It's Mr. Nelson, Wednesday, April 13th. And I want to give you a little introduction and tutorial on the Big Bang Theory, which is what you're going to be studying today, as well as Friday this week. Last week, you were expected to complete the Hubble's Law Lab, and that's the foundation of everything we're going to do this week. It's the foundation of the Big Bang. The fact that the universe is expanding at some accelerated rate, the Hubble constant, and that you can use that rate of expansion to determine how big the universe was in the past. Run it and rewind and figure out the amount of time it took to expand to its current state. Then you can begin to look back and say, hey, when did it begin? When was that first Big Bang, that beginning of expansion? And when you do that, you're starting to describe the fact that there was a beginning. That's a big idea. That question couldn't have been asked in the past. It used to be thought that the universe had always been. It was eternal. It was static, unchanging, forever. The old Einstein view of the universe, which was here, just the Milky Way galaxy. This is an image of the Milky Way. And we, on Earth, in our solar system, are about halfway out along the radius of a spiral arm from the nuclear bulge, the center of the Milky Way galaxy, which is a supermassive black hole, over 4 million solar masses at the center. We're about 25,000 light years out. It's about a 50,000 light year radius. And what we know now is that from our view, if we look above and below the galactic plane, the northern and southern galactic hemispheres, looks kind of similar on a large scale, the universe. If we look in every direction, the universe looks like the same everywhere. And that's a bit of a mystery. And this leads to this idea that we call the cosmological principle. And that is the fact that on the large scale, the universe is both isotropic and homogeneous. Now, those terms are a little strange. So you're going to be reading section 26.1 and 26.2 in the book, which describes the universe on a large scale. It describes the cosmological principle. And essentially what it means is when you say the universe is homogeneous, that is to say if you take any chunk of the universe, it's about 300 megaparsecs by 300 megaparsecs, any square block, any cubic block really, 300 cubic megaparsec volume of space. It's basically the same density, the same temperature, the same amount of galaxies per unit volume, everywhere. And that is to say, there's no special place. There's not one region of the universe can claim to be the edge of the universe. Not one region of the universe can claim to be the center. If we look at it from our view, we will see the same. And if you look at it from any other view, any other point of view, you'll see the same. And to be isotropic means that no matter what direction you look in, up, down, left, right, it's kind of the same. You look above or below, it looks the same. These assumptions of the cosmological principle mean that there's really no special place. So if we take this view here, here's Earth, and we kind of look outward, each galaxy that we view is moving away from us on a large scale. On the small scale, like right around here, within the local group of galaxies that we reside in, less than 300 megaparsecs of distance, there's some blue shifting and there's some gravitational forces that cause objects to move towards each other. But on the large scale, we don't see that. Things are so large and so far separated that gravity is too weak of a force. And there's some other force causing everything to expand. So think of the universe as like it's inflating, it's filling up with air, it's inflating, everything's expanding from everything. And this expansion, we don't really understand what's driving it. We call it dark energy today. We don't fully understand what it is, but we think there's some anti-gravitational repulsive force that we now call dark energy that is causing this expansion. And the universe has gotten so large now that gravity cannot slow it down. And we think it's just going to continue forever. When you get into section 26.2, the other section you're going to read on the expanding universe, you're going to read about Olber's paradox. A lot of fun. And I'm going to leave that to you for the reading because there's some great questions on there. The question of why is it dark at night sounds like a simple question, but it's not a simple question if depending on the assumptions that you understand about the universe, if you think the universe was static, unchanging, finite in size, eternal, you cannot answer this question. But if you understand the current model of the universe, you can start to. So I have a little video posted about this as well. And last week, as you studied Hubble's law and you calculated Hubble's constant, h naught, this value, you found out that the recessional velocity to distant galaxies, the rate at which they're receding from us, is equal to this value times the distance away. The greater the distance, the greater the recessional velocity. There's a direct relationship between the distance to a far, far galaxy and how fast it's receding away from us. And they're all receding away from us. And this would be true from any perspective. In other words, if you were to live anywhere in the universe, from any galaxy, and you looked outward, you would see essentially the same thing. That all other galaxies are receding away from you. It's not a unique perspective from Earth. Earth is not in a special place. Earth is not the center. Everybody can claim to have that special place. And you learned that if you knew the rate of expansion, Hubble's constant, you all had different values for Hubble's constant. Today, it's around 70 to 71 kilometers per second per megaparsec. There's a little bit of uncertainty there. And that leads us to saying that, well, if it's been expanding at this rate the whole time, you could run it rewind and realize that the universe began close to 14 billion years ago. It's really about 13.8 billion years ago today. That's the accepted value. The universe is 13.8 billion years old. There in fact was a beginning of time. And that is what the Big Bang Theory is. At some point in time, the universe was so small, it was condensed into this primordial atom, this volume so small that all of its mass was compacted down into that tiny space of near infinite density, and then for some reason suddenly expanded. There was some sort of Big Bang. And from that point in time, we can sort of trace the current size, the current structure of the universe from what we observe today. And it's important to note that Hubble's law is the same no matter who is making the measurements. It doesn't matter if it's somebody living in the Andromeda galaxy, or somebody living in the Milky Way galaxy, or somebody living in some distant galaxy. The expanding universe, it's also important to know that it didn't happen at some point in space. It didn't happen at some point in space. It happened at some point in time. So it's essentially a beginning of time, not necessarily a beginning of space. And that's a hard concept. Because you can't suggest that, hey, that's the location where it happened, because if you look everywhere in the universe, according to the cosmological principle, the universe appears to be about the same density, temperature, overall structure everywhere. It doesn't look like, oh, in that area, that's sort of like less dense and cooler, and over here it's hotter and more dense. We don't see that. And this is a great model, the inflating balloon. You're also going to hear about the raisin bread model, where we describe how as the universe inflates and expands, that's the balloon or the rising raisin bread, that the distance between points on that, these coins, or if these are raisins, doesn't matter. The distance between every one is increasing. No two coins on the surface of the balloon will ever move closer together. They will always all move away from each other, continually as the universe expands. And no one coin on the surface of this spherical shaped balloon can claim to be the center, because if it's a surface of a sphere, think of the surface of a sphere, there's no center. Maybe there's a center inside the sphere, but we're talking about the universe is just the rubber surface surrounding the spherical shell. So if you use this rubber surface on the sphere, it has no edge, it has no center. That's the cosmological principle. No location in space can claim to be the center of where the Big Bang happened. No location can claim to be the edge, because if you go around over here, and then you imagine you lived on a coin on this part of the universe, you would still see the same thing from there, and you would think you were the center looking outward. And when you look outward and you might see as far as you can possibly see to the edge of your horizon, that doesn't mean that's the edge of the universe. That's the edge of your visible horizon. And if you place yourself at a point at that location, you can then imagine living and residing there, looking outward in all directions, and feel like you're the center from that perspective. Even though While that might feel like you're the center of your own perspective, you might look as if you're at the edge of another's perspective. So there is no center, there is no boundary, there is no edge. Every position can claim to be special, can claim to be the center, and therefore none of them are. And therefore there is no exact boundary. But just like the surface of a balloon, you can only see one side that's kind of in your visible horizon. That doesn't mean there isn't another side. It's just outside your visible horizon. Similar when you look outside your window. There is a horizon, how far you can see it. It doesn't mean that's the edge of space. That's just the edge of your visible horizon. That analogy is true for the universe. And so this can be a little tricky. The same analogy can be explain the cosmological redshift. As everything moves further and further away, as space expands, it doesn't just increase the distance separating galaxies on a large scale. It also stretches the light in which that is traveling across the vastness of space. And as that light stretches, it redshifts. It increases in wavelength. And we see that from all distant galaxies. That's the evidence of Hubble's law, the redshift, which you measured last week in your lab. Now, these concepts can be really challenging. They're not always intuitive. They take a lot of time to read through it. So read through section 26.1, 26.2. Take some time to understand the cosmological principle, the Hubble constant, the Hubble's law, how it relates to the Big Bang Theory, Olber's paradox, and then answer the questions that I've assigned through Mastering Astronomy based on this reading. Just the two sections, though, 26.1, 26.2. That's all we have time for. Okay, good luck.